everyone, I'm Janelle Bailey from Temple University in Philadelphia, Pennsylvania in the US. I'm delighted to talk with you today about mixed methods designs for astronomy education research. Obviously, this is a short presentation. We won't be able to cover everything, but I hope to provide you with a few resources at the end. So mixed methods is defined by John Cresswell as a methodology and a method to research in the social, behavioral, and health sciences, in which the investigator gathers both quantitative, closed-ended, and qualitative, or open-ended, data, integrates or combines the two, and then draws inferences, called meta-inferences, from the integration that provides insight beyond what can be learned from the quantitative or qualitative data. So in other words, what we're doing is taking pieces of what we're used to with quantitative research and adding qualitative pieces and combining those in a meaningful way to give us more information than what we would be able to otherwise get. What mixed methods is not simply gathering both types of data without integrating them. Simply a label to apply without careful consideration of the design. There are robust considerations that should go into doing a good mixed method study. It's not mixed model research. Mixed models are a particular type of quantitative approach that takes into account nested data. This is not that. It's not simply used for evaluation, although that is often where we see it. It has now moved beyond evaluation and is used in a number of different types of research. It is not simply the addition of qualitative data to an inherently quantitative design. In other words, don't just tack on a few interviews at the end. It is not content analysis such as scores or categories from qualitative data. So in other words, taking your qualitative data, your text, and scoring it and doing nothing else with it. Not saying that's bad. Just saying that's not mixed methods. And finally, it's not simply collecting multiple either qualitative data sources or multiple quantitative data sources and putting those together. Cresswell defines a number of essential characteristics of mixed methods studies: that they collect and analyze quantitative and qualitative data in response to research questions, that they use rigorous qualitative and quantitative methods, so each one has to stand robustly on its own as well as be brought together, incorporate procedures within a mixed methods design, integrate that qualitative and quantitative data into the design, draw meta-inferences from this integration, and include a worldview and theory. For the remainder of this talk, I'm going to focus on two of these essential characteristics: collecting and analyzing the data, and integrating the data in the design. So when we collect and analyze quantitative data, what does that look like? Our quantitative data are closed-end questions. So Likert scales, multiple choice questions, those sorts of things where your participants are forced to choose something from a selection that's provided. Quantitative measures tend to measure variables. We talk about variables such as knowledge or self-efficacy or interest. And those quantitative values that come out, or the data that can be produced, can be analyzed through various statistical means. Which statistics depend on the type of quantitative data you have and the research questions you're asking, but statistics are appropriate for them. In the case of qualitative data, we're looking at things that are open-ended questions that can come in the form of text, such as students' open-ended responses to a question or an essay. It can come from audio or video, like interviews, or it can be observations of a situation in which your participants are engaged. And you might analyze that data through a thematic analysis. There are three basic designs in mixed methods research. Convergent, sometimes also called concurrent designs, usually has the data collected simultaneously. And if they're not collected exactly at the same time, they're at least kind of treated separately as if they were pretty close. The qualitative and quantitative strands are analyzed separately first. You analyze all the quantitative in one way, you analyze the qualitative in one way, and then after both analyses are done, you compare and merge the results. One way that might be done is through data transformation. For example, you might be looking at student work and analyze it both for the themes about what they talk about in that work, but you might also score it on a rubric, which means you can then use the scores in a quantitative type of analysis or combine it with the quantitative data that you collected in other ways. Explanatory sequential has the quantitative data collected first and then the qualitative after that. And in particular, the qualitative component is designed to explain the quantitative findings from personal experiences. So you're asking your participants to help you understand why the quantitative results came out the way they did. It is often used to explain unusual or surprising results in more detail. The third basic design is exploratory sequential. In this case, it's the other way around. You're doing your qualitative collection first and then your quantitative. The qualitative component is used to explore the ideas, figure out how to ask the questions that then are used in the quantitative data collection. This is often used for instrument development or to adjust existing instruments for cultural sensitivity and context. Okay, so in the case of the two sequential designs, it's not just about data collection, but also analysis. You have to do the first part of the data collection and analysis and use that analysis to inform the second part of data collection and analysis. Whereas convergent, you're treating them separately and then bringing them together after both are analyzed. So there are also complex designs that may incorporate one or more of these within a larger approach. And you may have other types of designs, such as quasi-experimental investigations as part of a larger mixed methods approach. That's a little beyond what we can do today, so I'll just leave you with that thought. So I've come up with a few examples of each type of design that are specific to astronomy education, or at least put in the context of an astronomy education research project. Okay. So in the first case, Dr. Cassiopeia uses a survey with both quantitative, such as the Likert scale, and qualitative, open-ended items to investigate students' perception of the new course design. In this case, the survey is being offered with both types of questions at the same time, but when Dr. Cassiopeia gets to doing the analysis, they're going to do the quantitative analysis separately from the qualitative and then look at how those results match up. In a second example, Professor Bellatrix analyzes classroom recordings, which are qualitative, from group work and compares them to the written work produced by the group, which is quantitative through scoring using a rubric. Finally, Dr. Andromeda interviews, again qualitative, teaching workshop participants about their experiences, which are combined with evaluation data, in this case quantitative, to determine the workshop's effectiveness. All three of these designs are convergent in that everything is happening at about the same time. So let's look at some explanatory sequential. In this case, Professor Aquila notices that some classes do better on a concept inventory, quantitative measure, than others, and interviews, qualitative, students to understand their background experiences. Ms. Polaris surveys, using a quantitative survey, faculty about their willingness to adopt active learning strategies and discovers several resistance points. And so then interviews, qualitative, key members of the department to find out how barriers might be removed. In both of these cases, you're taking quantitative data and figuring out how to use qualitative to help explain the existing results. One more example. Dr. Vega looks at our faculty members' course evaluations and next semester conducts observations and interviews, both of which are qualitative, to interview opportunities, to identify opportunities for improvement among interested faculty. All of those cases are explanatory sequential. You have the quantitative coming first and use the qualitative to explain the results. Final design is exploratory sequential. Mr. Mars conducts observations, which is qualitative, of his colleagues' classrooms to help develop items for a survey, quantitative, about active learning strategies they use in their astronomy courses. So in this case, Mr. Mars is using the observations first to get a sense of what's out there before asking questions that might lead to the number of strategies and the frequency of their use. In a second example, Dr. Corbus interviews students about their understanding of galaxy formation and evolution before developing and testing a concept inventory on the topic. As the developer of a concept inventory myself, I can tell you this is basically what I did. Finally, Professor Orion conducts focus group interviews, which are qualitative, about youth interest in astronomy and events before adapting an existing survey for local contexts. So in this case, maybe the original survey was developed in another country, and so may not be exactly applicable in the Professor Orion's context, and so they want to make it more applicable for them. These 9 examples are literally just things that I made up off of the top of my head, although, as in the case of Dr. Corbus' development of a concept inventory, they are all inspired by real studies. And these designs show how you can use both types of data in a complementary way. Once you collect the data, you have to come and integrate them together. And that's the tricky part. So the integration of the data can take a lot of different approaches. The key thing is that you're taking both the quantitative results and the qualitative results and putting them together in some sort of way. Now, sometimes that means data transformations. So for example, you might take your qualitative results and do frequency counts, or you might use a rubric to score written results and then use that with the quantitative. However, you might also look for things like groupings in the quantitative results. What are the types of faculty use of active learning strategies? Who uses what? And then use the qualitative results to provide examples of those different clusters or groups in your quantitative results. In all of these things, we have to think about what is our intent in integrating, other than just meeting the choices for a good mixed method study, but also how are we going to do it? This integration part, in my experience, and this comes from doing mixed method studies as well as teaching a course on mixed methods, is one of the most challenging pieces. But it's really what sets mixed methods apart from other designs, including multiple methods, which is where you just have both types in the same study. Integration of results is what really lends power to mixed methods designs and helps set you up for some really interesting things that can be built upon. So a few resources that might help you if you are interested in approaching astronomy education research through a mixed methods design. The Cresswell book at the first line is the one that I quoted from. This is a concise introduction to mixed methods. It's relatively inexpensive and small and straightforward. The next one, Fetters, is a nice little article that I believe is open access. It uses equations to describe the different types of mixed methods and how you might think about how mixed methods can contribute to the research in a way that's greater than qualitative or quantitative on their own. The same Fetters also wrote a book called the Mixed Methods Research Workbook, which has a series of activities to help you design, implement, and publish mixed methods studies. It's got some really practical steps and things to think about. And then Plano Clark has an article in Contemporary Educational Psychology called Meaningful Integration within Mixed Methods Studies, identifying what, why, what, when, and how, which has some great examples of thinking about that integration piece. Finally, there's a journal of mixed methods research. Now, this journal doesn't have a lot in the way of astronomy education, but it does have nothing but mixed methods design. So if you want to get a good feel for like what the designs are and how they're used and how they're written about, this is a great source to go to. So again, my name's Janelle Bailey. Thank you very much for listening in, and wish you the best of luck if you start to engage in mixed methods research.
Hello everyone, I'm Chad Lucas. I lecture for the Department of Physics and I'm a PhD candidate in the Department of Astronomy, both here at the University of Cape Town in South Africa. Previously, I did my undergraduate studies in physics. I also hold both honors and master's degrees in astrophysics. My research has focused on astronomy education, particularly student reasoning, and today I'll be talking a bit about this research which formed the basis of my master's dissertation. The title of my master's dissertation was Introductory Astronomy Students' Reasoning about Astrophysical Phenomena Within Their Observational Experience. Before taking a deeper dive into exactly what this research entailed, I want to first explain to you where it comes from. In other words, why I investigated student reasoning. So why investigate student reasoning? You see, Astronomy Education Research, or AER, has largely, not exclusively, but largely focused on identifying students' so-called misconceptions. Commons describe these misconceptions as being deep-seated beliefs inconsistent with scientific understanding, and further noted that these misconceptions tend to reappear even after instruction. Here the word instruction refers to teaching or lecturing in the case of a university. Given the fact that these so-called misconceptions often reappear after instruction, I felt the need to look at this from a different angle. Instead of thinking of these misconceptions as beliefs that are difficult to change, instead I want to frame it like this. Let's think of these misconceptions as being the endpoints of student reasoning. And then, given the fact that these misconceptions are well documented in the literature, I put forward the following question in my dissertation. Shouldn't we instead first seek to understand how students think or reason about astronomy concepts before seeking to influence what they think or the outcomes of their reasoning? To investigate student reasoning, it requires that you elicit as much as possible from the students. I did this using questionnaires, but you could, for example, conduct interviews with students or hold group discussions. I combed through the literature and found no suitable questionnaires. In the literature, they are referred to as concept inventories, and essentially they test students' conceptual understanding of topics. In other words, they focus on what students think or the outcomes of student reasoning. Now, because I was interested in how students reason within the context of astronomy, I designed a new questionnaire, the ARQ, or Astronomy Reasoning Questionnaire. In designing the questionnaire, I first chose the topics that the questions would cover. Most of the topics included were informed by the IAU Big Ideas in Astronomy project. I focused on Big Idea 2. Why? Well, because the sub-ideas contained within Big Idea 2 aligned closest with the objectives of the study, namely to probe student ideas and reasoning on astronomical phenomena that they experience observationally. In total, I included 8 topics in my questionnaire. However, I will list the 4 which are analyzed as part of this dissertation. So the day-night cycle, seasons, differences between the luminosities of stars, and why stars appear to twinkle. So how did I frame the questions? Well, research by Ali and Demari found that students' writing was highly dependent on perceived audience, and students were more likely to engage in meaningful and critical thinking if their perceived audience was a friend or peer, in other words, someone who the student perceives as knowing less. Alternatively, Ali and Demari found that when the students perceived the audience as being someone who knows more, for example, if they thought that they were speaking to a lecturer or teacher, that the student was then likely to experience feelings of nervousness and fear, in which case their cognitive abilities are often diminished. So here is an example question. Why do we experience day and night every 24 hours? This is a typical question, one that most of you may have asked or been asked before, but this is not how I phrased the question. Instead, I phrased this question as follows in the questionnaire. You must give a talk to a grade 10 class about why we experience night and day every 24 hours. write in detail what you would tell them, and you may draw diagrams to aid your explanations. Now, in this question, the university student is positioned as a knower. In other words, the student knows more. They are the proverbial expert in comparison to the school kids that the student needs to talk to. Now, the statement, write in detail what you would tell them, you may draw diagrams to aid your explanations. This statement I included on every page with every single question. All other questions, which I'm not showing for time, were phrased similarly. I administered the questionnaire to the first year astronomy students on the first day of class at UCT, the University of Cape Town. And then, of course, because this research involves taking data from human participants, I obtained ethics approval from the university. And then the analysis followed the grounded approach, particularly the constructivist grounded theory method that was developed by the American sociologist Kathy Sharmas. Now, the first step in the analysis is to code the data. Here, the word code does not refer to the process of writing instructions for computers. No, instead it refers to the process of analyzing qualitative data. So you begin by reading a student response, identifying key phrases, which we then shorten into key ideas. And it is to those key ideas that I then assign numerical codes. I then look through all the other student responses to a question, and where that same idea is present, I assign the same code to those students. I then repeat the process, assigning new codes to new ideas as and when they arise. And then I create a tally, which in a nutshell allows me to say things like this: so many students said this, so many students said that. In this table, we see all the key ideas identified in student responses to the question on day and night. In the center column, we see the number of students who mentioned a particular key idea, and then also it emerged that many of these key ideas were similar, and so I grouped them into broad idea categories. Perhaps unsurprisingly, 95% or 39 of the 41 students mentioned Earth rotation in their answers as to why we experience night and day. More interestingly, though, 85% of the students added that the face of the Earth pointed towards the Sun experiences day, whilst the face pointed away experiences night. In other words, 85% of the students ventured further than simply stating, well, we experience day and night because the Earth rotates. In this image, I am simply showing you how the ideas were connected in forming the larger idea category, Earth rotation. Now, this image is interesting for several reasons. Firstly, if you look closely, you will see that the students express themselves diversely, and therefore we can say that they think in diverse ways. Secondly, students experienced difficulty with terminology. Many of them used the words orbit, rotate, spin, revolve interchangeably. Now, ordinarily in a test setting, they might be marked wrong, but because they were encouraged to write as much as they could, you could see that they knew what they were trying to explain, even when their vocabulary wasn't correct. One of the other questions I asked the students was to explain why stars appear to twinkle. Now, twinkling is not taught in school, and this was the first day of class, so what they said is likely to be their own ideas. Again, many ideas were identified in the student responses, and I was able to group similar ideas into large idea categories. So here's an example. 20% of students explain twinkling in terms of the energy generation in stars, and you can even track a reasoning chain here. So some students said that these chemical reactions in stars produce light, and fluctuations in these chemical reactions causes fluctuation in the light intensity. This in turn we then perceive as twinkling. Here is another category of idea which emerged in the student explanations on why stars twinkle. So 20% of students explain twinkling in terms of interferences along the line of sight. For example, some students say that light from stars is a constant stream, and that there's gas and dust that passes between the star and us, thereby blocking the light and interfering with the light, which in turn we perceive as twinkling. So why do stars actually twinkle? Well, it's due to Earth's atmosphere. Earth's atmosphere is windy, it's turbulent, and so it has a tendency to refract light from faraway objects like stars. Sadly, only one student was able to offer the correct explanation to this question, but there's a bit more to it than this. So, what was more interesting was that the students provided rich, detailed explanations, and this revealed a depth of thought and engagement. Of course, this is often masked by multiple choice questionnaires. And although many of the students failed to produce correct explanations to concepts they had not yet been taught, most of our students offered well-reasoned, plausible explanations. You see, they engaged in logical sense-making. So in conclusion, reasoning is the hallmark of scientific thinking, and I encourage you to foster spaces where you encourage this. When students are wrong, probe why. Simply stating they are wrong may diminish their ability to reason. You see, when you don't say why they are wrong, they may conclude that their reasoning is flawed, where in actuality they may have engaged in sound, sequential logical reasoning, however based on incorrect starting ideas. So, praise the ability to reason, but probe the origins of the ideas when the explanations don't align with yours. Thank you for listening. I'm of course more than happy to take any questions, and you are more than welcome to email me on the address provided.
Imagina que comienzas tu carrera como profesor de astronomía. Tu primer día es en un salón de clases lleno de estudiantes ansiosos por aprender sobre el universo. Pasado el tiempo, unos 20 años después aproximadamente, estás a punto de retirarte. Y tu último día también es en un salón de clases, habiendo salido poco o nada de este tipo de ambiente. Un saludo para todos. Mi nombre es José Antonio de Santiago García. Soy profesor de Ciencias de la Universidad Nacional Experimental Rafael María Baral, Menegrande, Venezuela. Y hoy quiero mostrarles cómo he transformado esa experiencia tradicional en algo más dinámico y enriquecedor con mi proyecto, el cual lleva por nombre el título de la charla de hoy: Innovación en la enseñanza de la astronomía, un estudio de la aula invertida y el peripatetismo astronómico. Este estudio explora la combinación de dos metodologías innovadoras, el aula invertida y el peripatetismo astronómico, como herramientas para transformar la enseñanza de la astronomía. El enfoque principal de esta investigación se centra en evaluar cómo estas metodologías influyen en el aprendizaje, la participación y el interés de los estudiantes. En nuestro club de astronomía hemos implementado estas metodologías con el fin de crear un entorno de aprendizaje que no solo favorezca la adquisición de conocimientos teóricos, sino también la experiencia práctica y reflexiva de la astronomía. Como ya les mencioné, estas metodologías las hemos implementado en nuestro club, el cual lleva por nombre AstroSí y fue fundado hace 1 año y medio. Y es en este entorno donde hemos obtenido resultados muy positivos. Es acá donde hemos puesto en práctica estas metodologías. Pero bien, veamos, ¿qué es el aula invertida? En esta metodología, los estudiantes asumen un papel autónomo en la adquisición de conocimientos teóricos en sus casas, a través de recursos digitales como videos, lecturas y cuestionarios en línea. Esta preparación previa les permite llegar a las sesiones presenciales con una base teórica sólida, lista para ser aplicada en actividades prácticas. El peripatetismo astronómico está inspirado en las enseñanzas aristotélicas. El peripatetismo astronómico lleva la instrucción al aire libre, donde las caminatas nocturnas y las observaciones del cielo facilitan una enseñanza inmersiva. Los estudiantes utilizan telescopios, mapas estelares y aplicaciones móviles para observar constelaciones y otros cuerpos celestes, permitiendo la conexión directa entre la teoría y la práctica en un entorno real. Implementaciones en nuestro club de astronomía. Las sesiones del club se organizan en 3 fases clave. Hay una preparación teórica en casa. Los estudiantes acceden a materiales didácticos en línea que cubren los conceptos astronómicos esenciales. Esto fomenta su autonomía y les permite llegar mejor preparados para las actividades prácticas. Tenemos sesiones prácticas al aire libre. En estas reuniones se realizan caminatas nocturnas y observaciones astronómicas bajo el cielo, donde los estudiantes aplican lo aprendido, identificando cuerpos celestes y discutiendo los fenómenos astronómicos observados en tiempo real. Tenemos discusiones y reflexiones. Tras las actividades prácticas, los estudiantes participan en debates y reflexiones grupales, donde comparten sus observaciones y plantean preguntas, promoviendo un aprendizaje colaborativo que profundiza su comprensión. Para evaluar el impacto de estas metodologías en el aprendizaje de los estudiantes, utilizamos una combinación de técnicas cualitativas y cuantitativas. Utilizamos cuestionarios pre y post sesión. Aplicamos cuestionarios antes y después de las sesiones prácticas para medir el progreso en la comprensión de conceptos teóricos y su aplicación práctica. Hay una observación directa. Durante las sesiones al aire libre se realizaron observaciones sistemáticas de la participación de los estudiantes. Se documentó la capacidad de los estudiantes para identificar cuerpos celestes, la calidad de sus intervenciones en las discusiones y su habilidad para conectar conceptos teóricos con las observaciones realizadas. Tenemos también entrevistas semi-estructuradas. Al final de cada ciclo, realizamos entrevistas con los estudiantes para recoger sus percepciones sobre las metodologías implementadas, la relación entre la teoría y la práctica y el impacto que éstas tuvieron en su motivación y el interés por la astronomía. Nuestro objetivo fue observar cómo estas metodologías fomentan no solo una mejor comprensión de la astronomía, sino también una mayor conexión emocional con el cosmos. Queríamos identificar las áreas de mejora en el proceso de aprendizaje y explorar cómo el entorno natural y la autonomía de los estudiantes influyen en su capacidad para aplicar conceptos complejos en situaciones reales. Los datos preliminares recogidos a partir de esta implementación indican los siguientes resultados. Hay un aumento en la participación. Los estudiantes muestran un mayor entusiasmo y compromiso en las actividades del club, participando activamente tanto en las observaciones como en los debates. Hay una mejora en la comprensión. La integración de la teoría y la práctica ha fortalecido significativamente la comprensión de conceptos astronómicos complejos. Hay una conexión personal con el universo. El contexto al aire libre y las observaciones astronómicas han despertado un interés más profundo y emocional por la astronomía, generando una conexión personal con el universo que va más allá del aula. La combinación del aula invertida y el peripatetismo astronómico ha mostrado ser una metodología eficaz para mejorar tanto la participación como la comprensión de los estudiantes en astronomía. Nuestra investigación en el Club de Astronomía sugiere que estas metodologías no solo aumentan el interés y la motivación de los estudiantes, sino que también les proporcionan una comprensión más profunda de los conceptos astronómicos. Seguiremos, por supuesto, afinando y explorando estas herramientas para maximizar su impacto en la educación astronómica. Acá le traigo de manera reflexiva estas líneas. Enseñamos a nuestros estudiantes sobre la inmensidad del universo, pero no salimos del aula de clase. Gracias por escuchar. Ha sido un placer.
My name is Oriole Marshall, and I'm a PhD student at the Universities of Copenhagen and Antwerp. And today I'll be talking about the insights into science teacher partnerships during the creation of exoplanet science lessons. To give you some context, I'm part of a research network which looks into modelling protoplanetary disk and exoplanet climates and atmospheres. And what I'm doing as my project is translating those into educational materials. And so I wanted to focus today on the specifics of this initial development stage. The method that I used for creating these was using scientist-teacher partnerships. This is the idea of collaborating with scientists and teachers. So the scientists that we're working with are the 13 PhD students who are doing a straight astrophysics PhD as part of my network. And then the teachers we're working with were 5 geography and physics teachers from Flanders who were volunteers. And so through this collaboration, we created a set of inquiry-based lesson materials. And the reason that we chose inquiry-based science education is because it's student-led, mimics scientists' actions, and it's very hands-on learning. And because one of the purposes of this project is that we're integrating contemporary research into the classroom, that we felt that having the students mimic scientists' actions was an appropriate parallel for the research going on within the scientists' work that we're bringing in to these materials. So the theory that I'm using for this project, that I'll be mapping the scientist-teacher partnerships idea onto, is the model of educational reconstruction. This is a model which is often used for creating educational materials based on contemporary research, so modern topics that aren't yet in the curriculum. And this is built upon 3 pillars. So there's the bottom left here looking at the analysis of science content and structure. And then on the right here is looking at analysis of student perspectives and learning processes. And then at the top, there is design and evaluation of learning environments. For this talk, I've summarized these into scientific input, pedagogical input, and lesson design. And these are going to be covered by the scientists, the teachers, and myself, the educational researcher, in this sort of diagram where they're all interplay with each other. And I've broken down the sort of activities, the steps within this partnership into a few key elements. So we have interviews with the scientists, familiarization with research topics, and individual feedback from the scientists. And then mirroring this is interviews with the teachers, reviewing existing educational materials, and individual feedback from the teachers. And then in the lesson design, we have some independent theory-driven development, and then some co-development with the teachers and scientists, which is where this scientist-teacher partnership really comes into play. The timeline here, this shows the different activities and how they're broken down. It's shown very linear here, but this was a design-based research project, and so the last few steps, particularly the development and feedback, was much more iterative. There were many cycles of it, but it's shown linear here just for ease of viewing. First, we'll look at the initial interviews and familiarization with research, where this is the initial collaboration between the scientist and myself. We had interviews with each of the 13 scientists, and I haven't done the full analysis that I'm going to show here. I'm just going to show you a very broad overview. So we coded all of the notes from these meetings, and the topics that came up the most often with the scientists were models and simulations, atmosphere, clouds, and planets, which makes sense given the topics of this network. So I then went on to familiarize myself with the sort of content of this lesson being clouds and lightning in an exoplanet setting, as you can see from some of these images that are output from the network on the right. So this is clouds and lightning, respectively. And then we used this initial sort of topic selection and went on to look at some interviews with teachers. So we asked them about these topics and sort of what their thoughts were about bringing these into the classroom. The top 5 topics that were discussed by the teachers during this was the scheduling and the level. So scheduling being sort of practical matters about the timing in the lesson and their timing within the school structure. And then the level here is referring to presenting the materials at an appropriate level for the audience with which they're going to be taught to. And then some more broader topics such as astronomy, physics, and geography. I then also went on to have a look at Azero, Astro-IAU, and ESA Teach with Space to look if there are any existing resources in this field. Based on these first two sort of interventions, we then went on to do some independent theory-driven development. We looked at the overlap between the two, looking at sort of triboelectric charging and electricity and static electricity for the lightning, and then looking at cloud formation, condensation, nuclearization, and saturation, humidity. And so I started creating some ideas for activities that could be done in the lesson. And then we went into the co-development, and I showed these prototypes to the teachers and scientists in order to get feedback on the prototypes and the lesson structure and the scientific validity of it, so that we could improve and develop this lesson together. We created two different scientist-teacher partnership groups. One was focused on the clouds, which had a geography teacher and 3 cloud scientists, and then one that was focused on lightning that had a physics teacher and 2 lightning scientists, both looking at exoplanets, naturally. And so in the previous section, I was trying to focus on the sort of overlap of the two, so where they both joined together, so we could choose an appropriate topic that would suit them both. Whereas now in this co-development, it wasn't just about where we overlapped, and also not just about the scientists and the teachers, but also as my own input as an educational researcher. But we were also looking at the individual strengths that both bring. So if you remember, the scientists talking more about specifics and atmosphere and modeling, and then the teachers looking more at logistics and the level and sort of practicalities within the lesson, and then myself looking at a sort of more broader holistic view and acting as mediator between the two. So through these, we created these sort of physical models that could be used in the classroom that fit both practical, pedagogical, and scientific criteria presented by all the participants. And then we went in to test these out and get feedback from the participants. So we had on the left here, you can see the scientists trying out the models and giving written feedback on the materials, and then the teachers trying them in the lesson and having interviews with myself afterwards. And so through this process, we resulted in this set of lessons, which you can find online if you're interested. But overall, what I wanted to sort of take away from this is this idea that you can really look into getting not only the best of the overlap between them, but really benefiting from all of the qualities and skills that each people present in this group setting. And I think that scientist-teacher partnerships can be a really beneficial way of integrating topics such as astronomy topics like exoplanets into the classroom in a way that is valuing all of the different voices within this. Thank you very much for your attention, and I look forward to hearing your questions.